Our first speaker will be Robert Rosati from UT Austin, and he will tell us about rapid turn inflation, supergravity, and how rare and tachyonic they are. Please, Robbie, go
ahead. Yeah, thanks for inviting me, and thanks to the organizers and yeah, my co-authors also for working with me on this project. Vikas and Sonia are at UT Austin, and Roberta and Yvonne are at Swansea. And right, we started looking into rapid turn inflation, supergravity. As we know, cosmology, modern cosmology is pretty well described by single field scalar inflation. It matches, cosmic microwave background very well. But theoretically, a single field inflation requires a very flat potential. And these slow roll parameters related to the first and second derivatives of the potential need to be small in order for single field inflation to occur and to last sufficiently long. But as we know, especially in this audience, I'm sure we know, that there are quite a few constraints on the scalar potential from theoretical considerations. Very small masses are likely to experience quantum corrections. It's the eta-problem. And as well, you might not even have the small masses to start with if the de Sitter conjecture or something like it is true. Essentially forbids this ordinary kind of single field inflation. And as well, we know that supergravity models tend to have tachyons at near flat points or de Sitter points. Yeah, all this makes single field inflation seem pretty theoretically unmotivated. So we thought we should look into multifield inflation, and sort of in full string theory, we could start with supergravity. So the basic setup for multifield inflation that we took is just a bunch of scalar fields minimally coupled to gravity. The fields have an arbitrary kinetic term of this form. We take the physical space to be FRW. And as most of you probably know, we get accelerated expansion when the potential energy dominates when this epsilon ratio is less than 1. And the way multifield inflation can help and break this dependence on the potential being so flat is expressed here. So here, this eta parameter is not the same eta. This one just measures how quickly the epsilon parameter changes. But the interesting one for multifield inflation is this omega, which you can think about as the amounts of non-geodesic travel in the trajectory. If your fields had a canonical kinetic term, this would just be how straight or curved your trajectory is. But in general, it's just how closely does the trajectory track a geodesic in the using the kinetic term as the field space geodesics. So if you have single field inflation or slow turn inflation, everything in these curly brackets is 1. And your epsilon parameter that governs expansion is directly related to the shape of the potential. If you have significant turning, however, that doesn't need to be the case. And in some previous work that I've done with my collaborators, we worked out the complicated constraints from on the potential from rapid turning. And yeah, multifield inflation can also match observations equally well, and include some new signatures in gravitational waves and oscillations in the CMB, things like that. And one particularly nice way to get rapid turn inflation is called fat inflation, which some of my co-authors worked on before. And the basic idea is possible to show with the inflationary equations of motion that this element of the Hessian that's pointing along the trajectory is always proportional to the turn rate squared. So if all of the eigenvalues of the Hessian are significantly big, then you're guaranteed to have this one be large too. That's essentially the idea. And as well, because all these things are large masses, they're not sensitive to quantum corrections. So you also avoid the eta-problem at the same time. And the yeah, here sigma is the trajectory direction, and s is an orthogonal direction. And you can show that if this orthogonal direction is sufficiently small or tachyonic, then you will have a tachyonic eigenvalue as well. So if we have fat inflation, this mass will be larger than 9a squared. And this is one way to have rapid turn inflation, but it's certainly not the only. Yeah, orbital inflation, for instance, always has masses with a split sign. And a lot of the models I'll talk about today also have split sign masses. Okay, so now that we know that rapid turn inflation is interesting and that we should look for it in supergravity, how can we find it? So my collaborators and I, we started looking for these things in quite a few models in the literature, in both blind and directed searches. In some previous work, collaborators and I figured out, at a given point, how do you construct a rapidly turning trajectory if one exists? So we could use that solution for some of the models, or as well, we scanned without it. And I have a Julia package for doing multifield inflation and finding these trajectories. So we input all our models into my package. We scan them with a differential evolution optimizer, which is a fairly recent and pretty efficient optimization algorithm for high dimensional spaces. And the idea is we just minimize this cost function here as a function of the field's initial field values, initial velocities, and all the parameters in the Kähler and superpotentials. And we essentially just ranked inflationary trajectories by the number of e-folds. So the more, the better. The more, the smaller cost, and the turn rate. So the more turn rate, the smaller the cost as well. So we ended up scanning 17 models in total, most of which were from the literature, but we made some by hand as well. And these had 2 to 4 real fields. And of the models in the literature, only one of them had an order 1 turn rate that we could find. And it was really quite difficult to find. We put in these ad hoc models just to see how much you really needed to get rapid turn. Just like putting in, I'll talk more about them later, but putting in something like a polynomial or a series of exponentials as the superpotential with no theoretical motivations. Yeah, we also tried many other cost functions that didn't really change the results here. Okay, so let's try to set that up theoretically and understand a little bit what these high, medium turning models that we found. Okay, so for our supergravity inflation, we'll take a pretty standard action here with the Kähler potential and superpotential. And to get inflation, in principle, you could have any number of superfields. A single superfield or S Goldstino inflation is pretty different. It's pretty difficult to make happen, at least with rapid turn. So we looked at 2 superfields. That's kind of the minimum number. And as well, when inflation occurs in the direction orthogonal to the Goldstino, this is an attractor. It's always possible to make that happen. And we didn't look into having more superfields, but this is a low dimensional attractor. So if you have more, you're likely to hit the situation we studied. Okay, so in orthogonal to the Goldstino, we have 2 real fields. For now, I'll just call them R and theta. And we'll pick the field space metric to look like this purely conformal metric, which really isn't very restrictive in 2 dimensions. Quite a few things can be written this way by suitable field redefinitions. So these are the equations of motion here. And depending on which terms are small, you can get different kinds of inflation. So if you set theta prime to 0, this is moving purely along this axion. And this is very single field by the way this, you can tell because the whole other equation drops out. And an example of that is this reference. But it's not interesting for us because it's not rapid turn. Another idea is inflation purely along the axion. So you drop the R prime terms. And the nice thing is that this matches a lot of the field theory examples we have of rapid turn models that weren't necessarily from a UV motivated perspective. Yeah, including sidetracked inflation, orbital inflation, hyperinflation. And these equations of motion, now they both depend on theta prime, so you can require them to be consistent with each other and figure out where the inflationary trajectory is. And all you're really assuming here is slow roll and guessing the direction of the trajectory is approximately along the axion. And in principle, you don't have to do that. You could just look for general solutions, but the axion inflation solutions are a little more interesting because we know geodesics in this field space tend to go along axion directions. So if you're looking for non-geodesic trajectories, you should look along the axion. Right. Okay, so we studied this multifield axion inflation in a bit more detail. Because we're essentially assuming the direction of the trajectory, we can compute the quite a few things. We can compute the turning rate, for instance, in terms of the real fields or the complex fields, and the Kähler potential. And here, this epsilon t parameter, it's similar to epsilon v, except it depends on the projection of the potential along the trajectory. So it's small during inflation. And as you can see here, this epsilon t depends on the real potential and is particularly sensitive to the superpotential, while the turn rate is very sensitive to the Kähler potential. So you can kind of try to build models where use the superpotential to set slow roll and the Kähler potential to set rapid turn. Okay, so let's look at two of the models that seemed interesting in our numerical scan of the supergravity models. This one we called the no scale inspired model. So it's a very simple Kähler potential. And when this alpha parameter is exactly 1, that's no scale supergravity. And the superpotential we took to be of this form, but the exact form of this f function isn't really important for these conclusions. And we took, several forms of it, polynomials of arbitrary order, things like that. You can show that the turn rate is exactly related to the Ricci scalar of the field space, which is just constant in this case. So you really need quite a high curvature to compensate for the epsilon being small in order to have a high turn rate. And in this case, we're able to rule out fat inflation because we're able to compute the mass along the orthogonal direction to the trajectory, and show that it's when epsilon is small, it's also negative, and when alpha is small. And here's just a few plots of this turn rate for different values of alpha. As you can see, the smaller it goes, the higher the turn rate. The other model we looked at was an old one from Ellis et al. We call it the EGNO model, as the author's names, initials. And is a very similar superpotential, but the Kähler potential is quite a bit more complicated. And the Ricci scalar in this model can be very positive or very negative depending on location and field space. But the interesting thing is it has a kind of a sloped valley that supports order 1 turning pretty much everywhere, and it's not very sensitive to initial conditions. This is kind of what trajectories look like in the EGNO model. And so off to the left or right of this plot along R, the potential does horrible things. It's ADS and very steep. But along this region, it's gently sloped and high Ricci curvature. And there's this P parameter in the superpotential that sets this angle of this term. And whenever it's a multiple of pi, we saw higher turning in our scans. That's all that plot is. Yeah, and along the trajectory, the Ricci scalar is, relatively small and positive, but here's just a scan going from left to right over that region we saw. So the trajectory is happening near these little positive bumps. And similar to the other model, if we shrink alpha, we can increase the churn rate, but it's order 1 without doing that. Okay, so those are the only models we found with large churn rates. Well, even with significant effort, looking for other supergravity models with rapid turn inflation. Right, what do we learn? So we did develop a lot of new tools for finding rapid turn inflation and for scanning for inflationary trajectories just in a totally arbitrary setup, which is good to have. We learned that the assumptions we made about needing approximately axion inflation and moving orthogonal to the Scoldstino weren't really important numerically, at least. We didn't miss anything by making them. And all of these models seem to need a high field space curvature for a high turn rate. And we needed to set parameters like the alpha and the Kähler potential, which aren't really free parameters in string theory, right? Things that probably should be order 1. And fat inflation was very difficult to find. Tachyons were always on the trajectory, which is kind of funny because these models don't really satisfy the de Sitter conjecture at all. There are plenty of points that are that are approximately flat and have positive masses. But that's not where inflation happens. Inflation seems to select regions with tachyons. So all this together, it's led us to think, okay, in well-controlled, theoretically motivated supergravity, you're going, if you have rapid turn inflation, it's not going to be fat inflation, and it's probably going to be pretty difficult to find. It'll be very rare. just because you'll need these parameters that should be order 1 to be quite small. Okay, that's my talk. Does anyone have questions?
Okay, thanks a lot, Robbie, for the talk. Yeah, are there any questions in the audience? Yes, David, please.
Hi, Robbie. Hi, can you hear me?
Yes.
Good to see you. Thanks for the nice talk and the nice work. A quick question: how bad is it to get a tachyon on your trajectory? Actually, because you said some of these models are okay with observations. So what about the tachyon? Is it a problem or not? I'm not sure to understand.
Yeah, my understanding is it's a problem from the point of view of the eta-problem. Like you aren't protecting yourself from quantum corrections. But observationally, it's not a huge problem. You can have totally Planck compatible models with tachyons. Yeah, that can work. If it's too much of a tachyon, then your perturbations can grow too large, and then you have issues. But we didn't actually look at the perturbations at all, and it's possible to have tachyons without large perturbations. So we'd have to look into it more to know how bad it really is.
Okay, thank you very much.
Any other questions? Oh, yes, Fabian.
Hey. Can you quickly comment on the fact that you included the number of e-folds in your cost function? So another thing you could have done is you could have put a cutoff and said, okay, as long as I get 50 e-folds or something, I don't care. Would this change the number of the number of inflationary models you can find if you put sort of 1 over n, if n is smaller than 50 and 0 otherwise, or did you balance this with this factor A, or?
Good question. Yeah, I didn't write it here, but that is exactly what we did. If we got at least 60 e-folds, then I cut off. I didn't look for more. I stopped the focused on the turn rate part.
Okay, thank you.
All right. If there are no other questions, then let's all thank Robbie again.